But right now, what we do is we go to the lab, we say it attacks here. And then once we know that, it's pretty easy to explain why. But we can't do it the other way. We can't look at it and say it will attack here. We're just not that good. If you got a problem with it, though, we can look at it later, take a look at it. Okay, so what we've done is we've done this strictly with acids. What happens is if you have an epoxide and you're going to do it with a base, the less hindered carbon is always attacked. So we're talking about it's SN2. Now, you got to be careful with this because when you see a tertiary carbon, you can't say the nucleophile will go there if it's basic. You could only say it'll go there if it's acidic because the mechanisms are going to be different. So if we take something like this, and let's add a base that looks like this. So this might be NaOET, like that. So this is the less substituted carbon. This attacks like this. By the way, when we do this, it will look like this, just like it looked with E2. We're using the strong base in its conjugate acid, but there's enough of this to make it react. So what will happen is these electrons will pop up like that. And then what that will do is it will give us a negative species here, and then here we'll have the OET. And finally, we're going to have the ethanol, and this will attack, and it'll be protonated. We don't have to do anything in this case. We get this, and we get this. And again, it's anti. All anti-orgo reactions have this structure. This structure is anti. The epoxide, it's anti. Oxymercuration, demercuration, it's anti. Now I'm drawing it in a way that makes it easy to see. This is not a legitimate way to draw it. I'm just drawing it to make it easy like this because there's obviously pre-rotation. So the question is, why is this the case? Well, what happens is with structures like this, you're going to have the nucleophile attack one of these atoms, and this is going to come up like that. And then when you're done, more often than not, these are carbons. That's the common pattern, but it works for a lot of other stuff too. So then you have your nucleophile here, and then your electrophile comes into here. So your electrophile comes in like that, and that is by definition an anti-addition, meaning it occurs in different planes. So the plane is here. The nucleophile attacks, in this case, on the bottom, and the electrophile attacks on top. And so we're seeing the same thing here. Now, if you have an epoxide, you have this structure. So you're going to have anti. So unless there's another reaction down the road on the test, if it's just one reaction, you know that you're looking for an anti-addition because there's nothing else that happens. Now, you may not be able to see it depending on the structure, but if you can see it, it's anti. Okay. So I'm now going to go through the book. There's a bunch of easy stuff. As far as the nomenclature goes, there are some names that are prepared for you so that this over here, This is called methoxybenzene, and that's a perfectly good name for it, but the IUPAC system calls this anisole. It's a special name for the ether. So that's what's going on here. There's a special name because it's so common, they call it. It depends on your teacher, whether your teacher thinks that crown ethers are important or not. Historically, they're very important, but the idea is that you can create a cyclic ether that can trap a cation. And that means that you can dump the ether into a solution, and that ion, if it's the right size, will be trapped by the crown ether. And they've used this to do lots of cool stuff. Now, here's an example. So here we have an ether, and the way they name this is there's 18 atoms. So it's 18. It looks like a crown, and it's got 6 oxygens. So this is 18 crown 6, and it's the most famous crown ether because it was one of the first ones developed. And what it does is it traps the potassium ion. And when it traps the potassium ion, it can make the potassium ion go into solvent systems where it would normally not go because it's ionic, but all this stuff is just going to be mildly polar with lots of carbons. So the idea is you can take potassium with some other species attached to it, which they haven't shown you yet, and you can get it to go into a solvent where it wouldn't normally go. And let me see if they talk about that or not, because I'm not sure what they'll do. Okay, so 18 crown 6 is not the only one they've developed. So here you see a whole bunch of them. And what they do is they trap different size ions. And people have gotten very clever with this. They've gone way beyond this and what they can do. And there is one professor at University of Miami that is working on this stuff. At least he's got it all over his wall outside of his office. Oh, well, here it is. You see, you can actually use molecules like crown ethers to act as antibiotics. They work very much like crown ethers. And we can actually design antibiotics this way. So I don't think this is on the test. I happen to think it's interesting, but let's go back to this. Okay. As far as preparing ethers, one of the ways of preparing an ether is by doing this. Now let me see where it is. There it is. Okay. The tert-butyl group like this and react it. Now that will not give us any ether. Can you tell me why? So what happens is this. We have a tertiary group along with a very strong base. So we end up getting elimination. Now, I'm not saying that the steric factor isn't part of it, but the bigger answer is that elimination is favored. You remember this stuff?
Yeah.
Because so much of Orgo 2 is Orgo 1. Okay. Now, some of it is alkenes, but the truth is SN1, SN2, E1, and E2, you've already seen it coming back. That's the most important thing to know right now in Orgo 2. So yeah, so what would happen is for this one, what we would end up getting is this here. This would grab a hydrogen like that. And when it grabs it, the bromine leaves. This would be E2. So that's the way you don't want to do